In Chapter 4, we talk about electric potential. So it seems kind of a switch that we were talking about force and we were talking about electric field, and both of those are vectors and they define the properties of our charge or our charge distribution. And now all of a sudden we're switching to electric potential. And so I like to relate it to when we were studying in the first semester when we were talking about momentum. And momentum has a direction and a magnitude, and then we would switch. Then we switched to energy, and we would talk about energy, and energy was a scalar. So I'm gonna kind of relate this to that, and the electrical potential is like kinetic energy. So electrical potential is a scalar quantity, and it's really useful to study electric forces and electric fields, and since it's a scalar, sometimes it's a lot easier to use, and so you'll see an electric potential is measured in volts. And so everyone has some experience with volts and how a battery works and things like that. At least have a little experience with it. So the electrical potential is given as the potential energy per unit charge. And so here on the graph we have the potential energy is given as V sub E. So that's potential energy per unit charge over Q. And so we can use Coulomb's law for the potential, which is kq over r, where r is the distance from our point of interest, or from the charge to the point of interest. And again, the units for potential are volts, which are joule per coulomb, right? Because potential energy is a joule and charge is a coulomb. So I have joule per coulomb, and that's equal to a volt. So electrical potential energy is analogous to gravitational potential energy, and this is how I can think about it. If I have a mass that's about to fall down, a certain height, so it's thrown off a cliff, it has a potential energy which is equal to mgh. Well, if I think about an equivalent example for charge and energy, so electrical potential energy depends on the charge. And the way I like to think about it is I intuitively know that the mass has potential energy and it's going to fall to the ground. Well, I think you can intuitively understand this too. If I think about having a positive charge Q next to a positive plate, this charge is going to want to go away from that plate here, so it's going to want to move this way. So it has potential energy. I would have to hold that charge up against that plate, and when I would let it go, it would run to the negative plate over here. So this positive plate would push it, and this negative plate would pull it. So it's the same idea. As the mass is being pulled to the ground, this charge is being pushed away from this plate and pulled towards this plate. And so therefore it has potential energy, or electrical potential energy. Potential also follows the superposition principle, meaning that if I have more than one charge or charge distribution, I can add up the individual potentials to find the net potential for my distribution of charges. Equipotential lines, these connect points in space at the same potential. So the green dotted lines here represent lines of equipotential here. So all along this green line, my potential is the same. And all along this green circle, my potential is the same. And so this is for a dipole. And if you notice, the green lines are perpendicular to my field lines. So my field lines are the red lines, but my green lines are the equipotential lines, so they're perpendicular to each other. If I look at my parallel plates here, I have field lines going to the right towards the negative plate, and I have equipotential lines are represented by the green dashed lines. And if I think about that, if I start at a voltage here on this plate of 20 volts, as I move across the separation between the plates, my voltage decreases from 20 volts down to 0 volts. So each one of these lines, this one represents 15 volts, this one represents 10 volts. And if I think about that, my change in potential here, so this is the change in potential, how much does it change from this 20 volts, this position at 20 volts to this position? And the way I can figure that out is I can say it changes by this amount, this E, my electric field, times my displacement, so the displacement along the electric field. So as I move from left to right here, my displacement is increasing, and so my potential here is decreasing. These are a summary of the equations that we need to know for electrostatics, and we have the ones that we learned in Chapter 1 and Chapter 2 and Chapter 3. The force is equal to KQQ over r squared in the r direction. The electric field is equal to KQ over r squared in the r direction also. So notice these have magnitudes and directions. Whereas my potential energy is KQQ over r, just a scalar, no direction. And my potential, phi, is equal to KQ over r. And this is just, this phi we can see is KQ over r. So this is phi is equal to V over Q. So these are scalars and these are vectors. So electrical potential, we can think about, like I said, the gravitational potential energy, where we have a positive value for potential energy if the where we'll lose potential energy when the object is released from that cliff. And here we have the same thing, that we have a high potential energy for a positive charge next to this positive plate. But as the charge moves away from the positive plate and toward the negative plate, we have our potential energy decreases. Now, if we have a negative charge here and we're near this positive charge plate, we have a low potential energy. And that's because this negative charge wants to be here. As we move the charge towards the negative plate, this charge doesn't want to be here. It's going to want to move back to the left. So therefore it has high potential energy when it's next to this plate. So negative charges move from low to high potential, whereas positive charges move from high to low potential. And just one more thing about capacitance. So a capacitor stores electric charge. And so we have the area of our plate here, and we see that a capacitor is going to be connected to some other object in a circuit. This is our distance, and often insulator material is added in between the plates because you can increase the voltage difference between two plates when you add an insulator. Some properties of a capacitor: the charge is equal to C, the capacitance, times the voltage. C, the capacitance, depends on the size, the shape, and the position of the plates. And we can calculate the capacitance by the information about our plate. So the surface area per plate, epsilon is our permittivity of free space, that's a constant, and D is the separation between the plates.